I'm going to now return to the concept of impedance that we met for a damped-driven oscillator, because it turns out that impedance is a pretty useful way to understand how waves work on different media. So we've got a driving force here, which is exerted by some sort of robot arm shaking the string up and down, and we've got a wave propagating out in the positive direction. And we assume the string's infinite, so we're not worried about back reflections or anything at this point. We'll assume a wave of the form y kx minus omega t, and we note that this form of the wave means that dy dt is equal to negative c dy dx. So you do those derivatives, you get a factor of omega on k, and that's where this phase velocity comes from. At x equal to 0, the vertical component of the tension in the string, so this string we assume has constant tension, capital T, the vertical component of that tension must balance the driving force. So if the tension is pulling the upwards direction, the force must be pulling, due to the robot arm, must be pulling in the downward direction to exactly balance that tension. Because we're thinking about driving an infinitesimally small mass here, so we want these forces to cancel, to first order at least. So the force provided by the robot arm must be equal to negative T, the tension, dy dx. This gives us the tension in the vertical direction for small angles at x equal to 0, which is the position of the robot arm. Using the result above, that's this result here, for relating the derivatives dy dx and dy dt, we can rewrite this as the tension times 1 on c times dy dt at x equal to 0. And dy dt, well, that's the velocity of the vertical velocity of the string at x equal to 0. So we can write the force applied by the robot arm is t on c times y dot at x equal to 0, or we can rewrite it as this, using the phase velocity as root t on rho. So here we have a relationship between the force and the velocity, and if you remember, that was exactly what we used to define the impedance. So for the driven oscillator, the impedance is defined as the ratio of the force and the velocity. So here we have z is equal to fy on y dot is equal to root t on rho, and this is known as the characteristic impedance of the string, and it depends on the tension and the linear density. Also, the impedance can be rewritten using the phase velocity here as t on c or rho times c. Let's now consider a string which is being driven over here, and we have a wave that propagates from that drive out to positive infinity in this direction. In this case, there'll be no reflection of the wave because it just keeps propagating along the string. What if now we want to terminate the string at this point here, x equal to d, and avoid reflection? What do we have to do? Well, let's consider the string in two parts. On this side we have the wave arriving. It's arriving on the string with impedance z1 at this point here, and the other side we're driving the string which has the same impedance, z1. So we have the relationship now between the driving force, which is the tension multiplied by the gradient with a negative sign in front, and the impedance of the string. And this comes from the previous slide in this relationship here. So it's a relationship between the force and the impedance. So the string is infinite. As I said, we have a travelling wave in the positive direction and there's no chance of a reflection. But now if we cut the string and we, instead of the string here, we just add some mechanical system with the same impedance z1, the string at this point here can't tell whether it's driving the remaining string with impedance z1 or something else with the same impedance, because it has the same mechanical properties. So we cut the string, take it away, and instead put in some sort of mechanical system here, which we want to have with the same impedance z1. And this is what's meant by impedance matching. If this damper here has impedance z1, same as the string, then it'll be driven and there'll be no reflection. All the energy is dumped into the damper. So what properties must this damper have? Well, the mechanical impedance of a damped oscillator is given by this, and we need this system here to have the same impedance as the string. In other words, we must have this equality here. So the impedance of the string, z1, is given by the square root of the tension multiplied by the linear density. So what that means is the mass must be 0 and the spring constant must be 0, because this is real, so these imaginary parts here must be equal to 0. And what we have is just the r, the damping rate due to the viscous fluid, say, in this damper, is equal to the square root of the tension multiplied by the linear density. So we can imagine this damper as being some massless piston that's pushing its way through some viscous fluid and gives damping but no mass and no spring constant.